Let's get the show on the road. All right, it's 4:30, last session of the day. I'm gonna get you out before beer o'clock. So, all right, with that, hello, welcome to Durable Data Storage with Containers. My name is Mark Bolinsky. I'm sure I've seen probably all of you at some point in the last few days. I'm Senior Technology Architect here at InterSystems, and today we're going to be going over how to achieve data durability for InterSystems IRIS in a container deployment setting, and also a little bit of a history lesson on containers itself. With containers, there are two general types of storage. There's ephemeral and persistent storage. Ephemeral is temporary, just as the name implies. The original design scope of a container is only persistent for the lifespan of the container itself. When a container is stopped, any data addition, updates, or deletes are gone with it upon restarting the container, and start fresh with whatever was originally composed within the container. There are benefits and use cases for this in an IRIS deployment. Application code, static stateless microservices, ESBs, or enterprise service buses, and even things like web servers or even IRIS ECP clients or application servers, or now as part of sharding, what we call compute nodes as part of a cloud scalability set. Persistent storage for containers is challenging, or it was, but it's necessary if you want to build a stateful app using containers. Mixing ephemeral and persistent storage strategy is generally not recommended, but there are some use cases where it is beneficial. Persistent volumes will be the focus for today. If you do have any questions, let me know. I'll throw the glow stick of destiny at you here so we can get it recorded. So just let me know. So brief history lesson on containers. Persistent storage was not originally part of the container picture. Docker containers were initially conceived as a here one moment, gone to the next. Resources didn't need persistent storage. A container would simply pop into existence, take whatever input received, do its job, pop back out of existence, handling off any output to whatever resource was supposed to make use of it or use it next. This is actually typical of the design and initial development phases of almost any kind of conceptual, innovative technology. The designers were quite reasonably assuming that existing well-established technologies, such as persistent data storage, would be handled by existing well-established resources. Does not need to be included in the design. Usually that's how it works. But as always, the devil's in the details. In the case of containers and persistent storage, the details include the practical need for some kind of storage for use by the container. Many common software tasks use temporary storage, while it may be possible to design programs that perform those tasks without the need for persistent storage. Doing so introduces unnecessary complications or prolonged use of individual containers. In practice, some containers remain in use for hours, or in this case of IRIS, hopefully days, weeks, months, however long. The longer the container remains in use, the greater the likelihood that it will need storage, either at a minimum, some sort of scratch pad, save state information, or even complex purposes. The need for containers to share data. This is the big one. Containers frequently need to work together, and working together usually means sharing data. And the easiest and best way to do data sharing is by offering some means of shared storage. Lack of such storage makes for sharing data difficult. So that's what the initial history of containers. It really wasn't meant, at least conceptually at the beginning, to be used for anything really durable, like a database management system or a data platform. Then when you consider containers on the move, so as part of an HA strategy, you can consider what happens if containers automatically moved from one server to another. Simple storage plugin or container volume typically bases its abstract storage system on the host system storage. What happens when a container is automatically moved from one server to another as part of maintenance or maintenance window or a downtime? This can be a serious problem for a container because depending on the system, containers may be moved around frequently as part of load balancing, node maintenance failure, or any other purpose for that matter. So you really need to plan for failure. Production workloads, having storage affinity for a container can certainly negatively impact a container's resiliency. But not necessarily, and I'll come back to this with some possible viable use cases later. But basically a plugin is running on a server, and if it points to a storage on that server, then the container which using it is no longer accessible, then you're done. There are options now available through CSI plugins such as Rook or Storage OS or even NFS for on-premise deployments that allow for abstracting the persistent storage volumes to move the containers when they are relocated. So the container storage link itself isn't broken and it's maintained. There's also having greater control. Persistent storage is ever increasingly abstracted and virtualized with layers of sophisticated management and host system storage resources down at the hardware level. A storage system might, for example, shift data between high-speed SSD storage to lower-speed archival storage, depending on the type of data and the containerized applications for quick needs. So that's getting into more of a traditional SAN topology, and having that access or availability to you outside of a container is very beneficial to maintain. And then there's also CSI and Kubernetes operators. This takes the step further to enterprise storage vendors such as Pure Storage, NetApp, Infinidad, EMC. Others have various plugins and also cloud storage solutions to allow you to continue to take advantage of these advanced storage capabilities traditionally found on on-prem solutions, which are now available in a public cloud setting. We have several storage partners here in the partner pavilion. Pure Storage, I know, is here. EMC, Infinidad may be here, I'm not sure. But they'd be more than happy to talk with you about both their Kubernetes integration and any cloud solution they have. Looking at standardized server storage, you can also expect to see virtualization of server-based storage. Virtualization of some sort would be less likely to be targeted for use of underlying hardware resources. It would, however, the effect of making such server-based storage even more generic and portable. Perhaps is the basic near future trend of persistent storage for containers. It will become more generic, more of a commodity and more universal. This is likely a welcome development for enterprises making heavy use of container-based operations, since it will simply simplify the deployment and use of persistent storage. In terms of a roadmap, for now, the situation remains complex and fluid. There is a variety of persistent storage solutions at play right now. This is one of those areas where any enterprise that's looking for the best and most durable solution is likely to consider benefits from expert advice from their container provider or cloud or storage partners. So history lesson aside and kind of general groundwork. So how persistent storage in a container in IRIS is considered. So at the root of it, separation of code and data is one of the primary advantages of containerization. A running container represents pure code that can work with any appropriate data source. However, because all application programs generate and maintain operating and historical data, such as configuration, language setting, user records, database files, log files, containerization typically must address the need to enable persistence of program-related data on durable data storage, because you certainly don't want it here now and gone tomorrow. In the case of InterSystems IRIS container, that mechanism is accomplished by following two things that are required. Saving a variety of instance-specific data for the use of the instance by in an upgraded container that replaces it, including log files, journal files, the write image journal file, the system databases that contain user definitions, and even security information and audit records. Also indicating where the data is stored, where it can be found when running and upgrading an image that's sitting on external storage to create that upgraded container. So how to accomplish this within and present your durability for your IRIS-based container? The Durable SYS feature, or the Durable persist feature, included as part of IRIS, does this by storing the needed data on an external storage or file system, which is mounted as a volume within the container and identified as an environment variable when the container is started. While the IRIS instance itself remains containerized, its instance-specific data is actually outside the container, just like databases, which an application data is stored, persisting it across container and instance restart. So you don't lose your data, which is pretty important. Configuration data consists of, when I say configuration data, it's more the iris.cpf, the iris.key, web gateway configuration, log files, and maybe even static files for a web application. And of course, basically, pretty much anything that's in the MGR directory, which houses the IRIS-SYS, audit, and several other of the databases that are supplied along with IRIS and the default write image journal file, which may be relocated if desired. It also contains the primary and alternate journal locations, which again is highly recommended to be configured to go somewhere else other than underneath MGR, which is the default. So what exactly is Durable SYS? It's a process that happens during initial container startup that essentially clones components of the IRIS instance requiring persistence and durability, including items such as, like I mentioned, the widge, %sys namespace, CPF files, blah, blah, blah. This feature is built into IRIS, and it's an automatic process. The cloning process is invoked by simply defining an environment variable called IAC_data_directory to a durable path, which is some kind of bind mount or mounted volume in your Docker or a persistent volume claim within Kubernetes. This also supports upgrades from version to version, even with the Durable SYS stored outside of the container. The process is seamless and it's transparent to starting the container. Simply declare the environment variable to your Docker command line or within your JSON file or the Kubernetes YAML file for your pod definition, and off you go. So here's the syntax using the environment variable with Docker run command. It's quite simple. On the first line with the -volume declaration, we declare external host. External_host is the host path to a durable storage location to be mounted by the container. Durable storage is the name for this location within the container itself. So it's the path. So you can give different names. They don't have to resemble the same path, what's external versus what's internal. On the second line, we have the IC data directory environment variable defined as durable_dir to the path of the durable SYS directory to be created in that location. There are various types of volume declarations options, as we talked about in our history lesson, and considerations about storage and host affinity come into play. But for now, we'll keep things simple and use the host path declaration, even though I said before it's really not recommended, especially when you're talking container portability and movability. We have a question. The question is for recording is for the environment variable set, can you have more than one set? Yes. As Connor mentioned. So here's a simple Docker command line example. And this example, durable SYS directory would be /data/IC iris_sys.d, which is outside the container, and /IC iris_sys.d within the container. You can name these whatever you want. You don't have to follow these. The environment variable, IC data directory, is the key component here. This coupled with the volume declaration is essentially what defines durable SYS to retain the configuration and stateful information of the IRIS container. Note that the trailing container image here with the XXX, these are just for reference or whatever the latest IRIS container build number that you want to be using to instantiate that container is in your repository. So there's no significance there to the XXX other than you replace it with what's appropriate. So Kubernetes takes it to the next level, and maybe you want to consider it an enterprise level, or at least maybe in my opinion. Kubernetes is carved up into layers and properly provides proper isolation between responsibilities and capabilities. In this example right here, we have, as part of step one, the administrator or storage admin provisions the physical volumes, or PVs. These volumes can be made up of different types of storage, different performance levels, or isolation of tenant within a multi-tenant environment. Step two, the user or whoever is provisioning the IRIS pod makes or creates a persistent volume claim, or what's known as a PVC. Step three, acknowledgement of the request will be received, assuming there isn't another claim against the same physical volume. And then step four, mount the PVC to your pod. So within the Kubernetes, it's pretty simple. Just like any other HA solution, you want to plan for failure because, after all, IRIS is a data platform and you want it to be resilient as possible. In this example, we have a simple 4-node Kubernetes cluster, and we have an IRIS pod running on node 2 with an iSCSI persistent volume claim to an external persistent volume. In the event node 2 failing, we want Kubernetes to relocate and restart the pod on another surviving node. The key to this is that the physical volume, the PV, is available to that node, as well as the persistent volume claim can be honored. So we see what will happen. Kubernetes restarts the pod on node 4, and the physical volume follows along with preserving the durable data we've associated with the pod, and ultimately the IRIS instance and associated databases and namespaces. Any questions so far? The question is typically how long will it take for a pod to relocate in a failure from one to the other? That's an operation and dependency on Kubernetes itself for its detection. Connor, you might have more thoughts on how quickly Kubernetes, but it's typically, if you're familiar with VMware HA and the heartbeating capable, it may be configurable, but I would think it's measured in seconds to maybe a couple minutes, but I'm not 100% sure on the actual time it takes. The recovery and the startup of IRIS itself in the container is pretty quick. The question is how long will it take to bring the application up in its entirety? It's dependent on your application itself, what additional startup routines you may have as part of whether you're using using zstu or %zstart to start additional processing. If you have any additional just health checks within the application, starting the pod itself is very fast, like seconds. So I wouldn't expect that just from a pure IRIS standpoint, it's not going to be significant by any means. So it's really dependent on the application and the type of IRIS pod it is itself. So if you're considering just an application server and there's really not a lot of data or updates associated with it, it's more of an ECP client or a compute node, there's nothing really to recover as part of the restart. Anything else? So there are numerous options for persistent volume types. The current list of supported types it's ever growing, and more storage solutions integrate with Kubernetes. The most common are the respective cloud providers' persistent storage offerings, such as AWS EBS volumes, Azure Disk as premium storage accounts, and Google persistent SSD with using Kubernetes in their GKE, EKS, and AKS managed solutions. On-prem solutions, the commonly used solutions are Fibre Channel, iSCSI, NFS, and even vSphere VMFS volumes. And when getting into hyper-converged or software-defined data centers, aka HCI or SDDC, you hear these terms used oftenly. Those architectures, solutions such as Portworx, StorageOS, Scale.io, and vSphere volumes, especially when using vSAN. There's also options such as OpenShift from Red Hat, which uses, I believe, Ceph, as well, to provide that data durability and cross-cluster shared storage aspect. So previously I mentioned Kubernetes persistent storage is defined as layers. These layers are storage class, the persistent volume, and the persistent volume claims. I'll give examples of these, starting with the storage class. The storage class definition provides a way for administrators to describe the class of storage that they're offering. Different classes may map to different quality service levels or performance levels, resiliency levels, backup policies, or the arbitrary policies determined by some cluster administrator. Kubernetes itself is unopinionated about what classes represent. This concept is just sometimes called profiles and other storage subsystems. In my example here, I'm just calling it my local storage. So here's the example YAML file that I've created for my storage class within a Kubernetes cluster. Next is the persistent volume. In this example, I defined a simple 100 gigabyte volume with an access mode of read write once. Read write once declaration means that the volume can be mounted as a read write by a single node at a time. This is important for IRIS as we never want to have multiple pods referencing or mounting a physical volume or a physical volume claim with a stored iris.dat file concurrently. Certainly will result in database degrades. I then, using a host path definition, again, not something that's recommended, but for testing purposes here, I'm showing it as an example because it's not really resilient because there is a node affinity. In this case, it's specific to coloperf AMD4 as the server. So far, we have our storage class defined. We have the physical volume created. The next step is to make a claim against the physical volume. Here we have the example of our persistent volume claim with the YAML file for Kubernetes and requesting the full 100 gigabyte from the physical volume itself. It's using the storage class I created earlier and requests the full 100 gigabytes. The final step is to then bind the volume claim to our IRIS pod. Here we have a simple IRIS pod YAML file using an IRIS 19.4 container with the persistent volume claim, loading our license key, and the reason for the session, our Durable SYS declaration. And it's all referencing the pod container's mounted path to the physical volume we just created. Super simple, right? Once we issued the kubectl or kubectl, whatever you want to call it, the kids call it something different, create using your YAML files. We see the pod is up and running, the PVC is listed, bound to the pod, everyone's happy, life is good. So, I'm sure you're wondering why I've been focusing and showing only a local on-prem stuff, and you're probably thinking, oh, isn't containers for, or pods just for cloud? No, not at all. Containers are not just for cloud, and cloud is not containers. Containers and even Kubernetes is, like I said, not for cloud. And sure, containers and Kubernetes are widely used in public cloud providers today and packaged up nice and neat as a service. However, I wanted to demonstrate that containers and Kubernetes doesn't require running in the public cloud. So if you have any data sovereignty or data governance regulations that prohibits the use of public cloud for the perception of data security, so there are on-prem solutions possible, and in some cases afford you far better storage performance and more storage services. Not that cloud storage is bad or slow, there's just always something better out there. And right now I would have been introducing John Owings from Pure Storage, but he's not here with us today. Pure Storage is one of our top storage partners, and I'm going to show a recorded demo, which hopefully works, of their Pure Service Orchestrator and their Kubernetes integration. So hopefully this works. So just a brief introduction of what their PSO or their Pure Service Orchestrator is. It provides an automated container storage on demand, scale across multiple arrays seamlessly, and that's great for high availability, upgradability. Both file and block on a shared infrastructure. So if you're using their Flash Array X or their Flash Blades, you can use both capabilities with their PSO. And there's also automatic failover for unattended service. So here we have Docker Volume Managed for the flash array, the flash blade, supports for standalone Docker servers, even dev laptops, support for most enterprise Linux, CentOS, RHEL, Ubuntu, CoreOS, Kubernetes Volume Management for flash array and the flash blade. And here showing what they integrate with. So let me, hopefully, you see that okay? And hopefully this works. So here it's going to list the Kubernetes nodes that we have in the cluster. So hopefully you can see that. So here we have all the nodes within our cluster. Then since we're using Helm to install PSO, let's run Helm ls to make sure there's nothing already running. It's not, we're clean. So here we can cat the PSO YAML install file, and all you need to do install PSO is need to know the array's IP and the API token, which we'll show right here, the IP address and the token. And then run Helm to install. So here we're starting with just a vanilla Kubernetes cluster, no storage presented to it, and we're now creating the Kubernetes integration of PSO from Pure's PSO into our Kubernetes cluster. So it takes a little bit. Okay, life's good, we're happy. And we see now that there's additional pods that have been created as doing the installation. So here now we'll show the IRIS YAML and the IRIS PVC YAML claim. I think. Yep, he's trying to. There we go. There's our claim and the IRIS pod definition. So here he's using only the community edition of, I think it's 19.2. And then there's the persistent volume claim. And now we're going to apply them. So now we'll have an IRIS pod running out on their cluster. And we're running. Our life is good, happy. So now it's going to go out and show that the volume is created on the flash array, just to show that it's an actual real thing out, a real LUN that's been created out on the array. And then he does have an upgrade process in here as well, but I don't think it works very well with the presentation. But so with that, I just showed that you can use on-prem storage with Kubernetes, presenting durable storage, not only at just the host layers or host volume, but also at an enterprise-grade storage solution. There was an option to demonstrate an upgrade of the array from one and non-disruptively move the pod from one node to the other. And then we're up and running. Are there any questions? It's beer o'clock, I think. So with that, here's some sessions for cloud, specific to cloud. I'm sure you've probably seen this a dozen times or so this week. And with that, I thank you, and that's it. I'll get you out of here early.